Hello everyone, welcome to this lecture series. Today we are going to talk about integration of a vector point function, and we are also going to talk about what are conservative fields and how we can calculate the line integral for such fields and the Green's theorem. So first is the line integral of vector field. So let you have a vector field f with continuous components defined along a smooth curve C parameterized by RT, where T varies from A to B. Okay, so F is a field with continuous components. Okay, so that means F, for example, in space can be written as having components in I, J and K direction. So F can be like Mi plus Nj plus Pk, where M and P will be functions of X, Y, Z, and it is parameterized. So X, Y, Z are functions of T, where T you may consider to be, say, for example, time. And the parameterization RT defines the direction, or you can say orientation, along this curve C, which we call the forward direction. Okay, so then the line integral of the vector field f along the uh, curve C is given by the integral f dot dr over the curve C, and the curve C is parameterized with t varying from a to b. So this can be written as integral a to b f r is a function of t, so we can just rewrite it as dr by dt times dt. Okay. Now this integral over cf dot dr is the vector differential form. Okay, and the corresponding here is the parametric vector form, or parametric vector evaluation of this line integral. Okay, so now we can solve this integral depending upon whether we want to solve it in parametric form, or we can solve it in the Cartesian coordinate form. Okay, so for example, if you are given the vector field in this form, which is uh, mi plus nj plus pk, where m and p are functions of x, y, z, and because r is a position vector which can be written as xi plus yj plus zk, so immediately this dot product can be written as mdx plus ndy plus pdz, and integrating over the c and by linearity of integral, this can be written as integral of mdx plus integral of ndy plus integral of pdz, and we can integrate with separately with limits of x, y and z. Okay, and if you want to solve it in the parameterized form, then since m and p are functions of x, y, z, and x, y, z are further functions of t, so we can just rewrite this. Okay, so if r is parameterized as this, x, y, z are functions of t, so say x is gt, y is ht, and z is p of t, then this can be easily written because dx will be g dash t dt, dy will be h dash t dt, and dz will be p dash t dt. So it immediately converts into mg dash plus nh dash plus p times p dash dt, where dash means derivative with respect to t. Okay, and integrating over t from this a to b. And so this is like the parametric scalar evaluation of this line integral. Okay, the uh, line integral is a scalar result here, and is also called the tangential line integral of the field along the curve C. Okay, so if this vector field f, if it represents a force throughout a region in space, then this line integral is defined to be the total work done by the continuous force field f, to move an object along this curve C from point A to point B, and if this field represents a velocity field of fluid flowing through a region in space, then this line integral over curve C, it represents the flow along the curve from the point A to B. Okay, so the line integral may be represented as a work done in moving an object, or it can be represented as a flow of fluid along the curve. Okay, okay, these two things. The integral represents the work done in moving object from point A to point B along curve, and if field is a velocity field, then the integral represents the flow integral, or the uh, flow along the curve from the point A to B. Okay, so if points A and B are the same points, okay, so if that means the flow is circular, okay, so we call the flow to be circulation around the curve. Okay, and uh, the circulation is considered to be positive, okay, if when we consider the direction to be the counterclockwise direction of flow. Okay, so if you are given a closed curve around which we have to find circulation, then the positive direction will be the counterclockwise direction. Okay, uh, this was dot product. If we replace dot product with the cross product, then the line integral is known as the vector line integral. Okay, so in that case the integral is C over C of the curve as vector field cross with dr. Okay, say for example, say find the work done by the force field, where force field is given this along the curve RT, which is given in parameterized form with t varying from 0 to 1 from origin to 1 1 1. Okay, so you can clearly see that x is t, y is t square, and z is t cube. So when t is 0, so it becomes 0 0 0 point, so that's origin. And when t is 1, so x1 y1 z1, so where it becomes 1 1 1 point. So this is a position vector for each point on the curve from origin to 1 1 1. And by when we if we have to calculate the work done by this field along this curve, then that means we just need to solve the line integral. So from the position vector we see that x is t, y is t square, z is t cube. So we can use that to write the field f in terms of the parameter t. Okay, so the vector field f is given by this, and we can just write it in terms of t, because we know that the position vector rt is xi plus yj plus zk. Okay, so immediately x is t, y is t square, z is t cube, which we can substitute. And rt is already given, so we can calculate its derivative dr by dt. So that will be I plus 2tj plus 3t square k, and where I, j, k are unit vectors along the direction x axis, y axis, and z axis. So we can calculate the line integral, okay, over c f dot dr as f dot dr by dt, where t varies from 0 to 1. Vector field f is known, dr by dt is known, so their dot product, okay, scalar product. So there is no component of I here, so I component dot product will be 0, because it will be like 0 I plus. Okay, so I coefficient is 0. 2tj times this dot product, so 2t times t cube minus t4 plus 3t square times this. Okay, and dot product is a scalar quantity, so we get a 0 to 1 this dot product with this, and so is 0 here, otherwise dot product is 1 but coefficient is 0. J dot j1, k dot k1, and the orthogonal dot products are 0. Okay, so we can easily rewrite this as 0 to 1 tq minus t4 times 2t. Okay, so that's this quantity, and t minus t6 times 3t square, so that's second. And so we can simply integrate with respect to t and substitute upper limit minus lower limit. Okay, so that gives us the work done by the force field around along this curve. Okay, so we take another example. Say a fluid velocity field is given now. Okay, and we have to find the flow along the helix, that means along this curve C, where t varies from 0 to pi by 2. Okay, so again, clearly you can see that rt is the position vector along this curve. So x is cos t, y is sin t, and z is t. And so I can substitute that here to write this in parametric form. So the vector field can be written as a function of t. Okay, x is cos t. Okay, y is sin t. So this quantity with k is sin t, and z is t. So this becomes tj. Okay, and dr by dt we can calculate derivative of with respect to t. Okay, so minus sin ti plus cos tj plus k. Okay, and so the flow along the curve we can calculate using the line integral. Okay, so f dot dr over the curve where t varies from 0 to pi by 2, f dot dr by dt, so their dot product. Okay, so dot product of these two, so it gives minus of cos t sin t plus t times cos t plus sin t. Okay, integration with respect to t, so we can integrate and then substitute the upper limit minus the lower limit. Okay, so cos 90 0, sin 91, so that gives pi by 2, minus cos 0 1, so that gives half, negative sign 0, this last quantity with lower limit. Okay, so pi by 2 minus half is the flow along the curve due to this fluid velocity. Okay, now we take the definition of path independence and conservative field. Okay, so we just calculated line integrals. Okay, and uh, we say that uh, but from a point A to B, okay, along a curve or along a path C which lies inside the domain. Okay, so what will happen if the integral along all curves? Okay, so you choose any curve from point A to point B, and the line integral over those curves remain gives the same value. Okay, if the curve lies within the domain, then we say that the line integral is in the independent of path. Okay, and the vector field will be called as the conservative field. Okay, so let f be a vector field defined on an open region D in space, and suppose that for any 2 points A and B in the domain, the line integral is given by integral f dot dr over the curve C along a path C from A to B in D, and it is same over all paths that we can choose from A to B. If this is true, okay, so if you have C is an arbitrary path from A to B, and so uh, over whatever path you choose from A to B inside the domain, if the line integral gives the same value, okay, over all the paths, then the integral is path independent in the domain, and the corresponding vector field is the conservative field on the domain. Okay, the word conservative comes from physics here, okay, which refers to fields in which the principle of conservation of energy holds. Okay, so uh, the idea is very simple, that if a field is conservative, then the line integral from A to B will be independent of path. Okay, so that means if you are given any 2 points A and B and we have to find the line integral from A to B, and field is conservative, so it will not depend on the path which is followed, because overall paths the result is same. So that means it will depend only on the endpoints A and B. Okay, uh, before we give the result, we'll just give you one more definition of a potential function. So if f is a vector field defined on the domain D, and if f vector field can be written as gradient of some function phi. Okay, we know del phi is gradient of phi, where phi is some scalar function on domain D, then phi is called the potential function of the vector field. Okay, so if you are given a vector field and if we can write the vector field as gradient of some scalar function, then the scalar function is called the potential function of the vector field. Okay, So now we'll give the fundamental theorem of line integral over the conservative fields. Okay, so let C be a smooth curve joining the point A to the point B in the plane or in space and is parameterized by this RT. Okay, so RT is the position vector for this curve joining the point A to point B, which where the curve can be in the plane or in the space. Okay, let phi be a differentiable function with a continuous gradient vector uh, f is equal to gradient phi. Okay, so let you have a scalar function phi whose continuous gradient vector, okay, is f vector. So f vector is the vector field such that it is gradient of scalar function on the domain D containing this curve C. Okay, then the line integral f dot dr is independent of the path and it depends only on the endpoints A and B, so it can be calculated directly from the scalar function phi by calculating the scalar function phi value at the endpoint B minus the value at endpoint A. Okay, so clearly that if you have a uh, field which is uh, conservative, then the results are independent of path, and in that case if you can write the vector field as a uh, in terms of its scalar potential, then the line integral will be independent of path and depends only on the endpoints and also on the value of scalar functions at the endpoint. Okay, at the value of the potential function at the endpoint. Okay, so line integral of the vector field if field is conservative uh, over any path from A to B can be calculated by calculating the value of the potential function at B minus the potential function at A. Okay, uh, a very simple example to show that find the work done by the conservative field. If you are given that this field is conservative, that means if I can write this as a gradient of some function where the scalar function is xyz, so clearly you can see that if I take the gradient of this, it will end up with this field. Okay, along any smooth curve C joining points A and B. Okay, so if this field is conservative, then the work done is the line integral, and that line integral is independent of path and can be calculated directly from the potential function at the end points. Okay, so this is the potential function fxyz is equal to xyz. So the work done, that means the line integral f dot dr, where f is this vector, can be calculated directly without solving the integral as this potential function at value at b minus the potential function value at a. Okay, so this is the, with this as the potential function, we have that f dot dr is grad f dot dr, and we can write it as potential function at b minus potential function a. B is 1 6 minus 4, a is minus 1 3 4 point, so that means xyz value at 1 6 minus 4 and xyz value at minus 139. So we can substitute xyz value and we can solve it to find that the work done value along C is given or is equal to 3. So it is easier to solve if you know that there is a conservative field, but then you need to know what is the corresponding potential function for that field. Okay, and if you know that and the endpoints, then you can find the work done. Okay, uh, this definition says that the conservative fields are gradient fields. Okay, so that means if you are given a field to be conservative, then the vector field f can be written as a gradient of some scalar function or potential function. Okay, so let f be a vector field which is given by mi plus nj plus pk, where m and p are continuous components, okay, throughout an open connected region D in space. Then the field is conservative if and only if the field is gradient field. Okay, that means field can be written to as equal to gradient of some scalar function phi for a differentiable function, this f. Okay, so that means if a field is conservative, then vector field can be written as equal to gradient of the scalar function, and the reverse converse is also true. If f vector can be written as a gradient of f, then it implies that field is conservative. Okay, so result is simple, because if say field is a gradient field, if f vector equals gradient of f, then by fundamental theorem the integral over the line integral f dot dr is fb minus fa. Okay, that means the line integral depends only on the endpoints and do not depend on the path, and so the field has to be conservative. Okay, similarly the reverse can be proved easily. uh, it results okay, in one important loop property of conservative fields. Okay, so the following two statements are equivalent. Okay, so if the line integral over the closed loop C is 0 around every loop, that is a closed curve C in D. Okay, then the field f is conservative of on D, or if field f is conservative on D, then the line integral over a closed loop is always 0. Okay, so say you are given a domain D, and in the domain D there are 2 points A and B. Okay, so let there are two paths C1 and C2 from A to B which lie within the domain D. Okay, if field is conservative, then the integral over C1 will be same as integral over C2, and because changing the direction reverses the sign of integral, so integral a to b over c2 is same as integral b to a over c2 with a negative sign. So a to b over c1 equals a to b c2, and if I change one of the integral, reverse its direction, so it will convert the positive to negative sign, and so they will add up to create a closed loop. So with integral value will become 0. Okay, so this immediately implies this. Okay, similarly, if you are given an integral which is 0 over a closed loop, okay, so say you are given this closed loop, and the integral of c1 minus the or plus the negative integral b2a over c2 is 0. Okay, and so if I reverse direction, so it will be negative of a to b, okay, over c2 paths, so they will become equal. Okay, so it will become path independent, and we can say field is conservative. Okay, so the two leads to the conservative fields are gradient fields, and conservative field has this property. So these three can be combined to write that these are if one of them is true, then all these three are true. Okay, that if field is a gradient field on the domain, then field has to be conservative, and if field is conservative, then the integral over any closed loop must be 0. Okay, and the converse. Okay, if the field if the integral over any closed loop is 0, then field is conservative, and if field is conservative, then field can be written as gradient of the scalar function f. Okay, uh, so now there are two questions which remains to be answered, that how we can prove that a given field is conservative. If you are given a vector field, say if you are just given this vector field mi plus nj plus pk, then how you can prove that this is a conservative field? And second, if you are given a conservative field f, can say if we said that this is a conservative field, then how we can find the potential function such that this is satisfied. Okay, so these two are satisfied or by this component test for conservative fields. So let f be a vector field on an open simply connected domain whose component functions have continuous first partial derivatives, then field is conservative if and only if this is true. Okay, the p derivative with y equals the n derivative with z. the m derivative with z is equal to p derivative with x, and n derivative x is equal to m derivative y. Okay, if this is true, then field is conservative. If field is conservative, then this is true. Okay, so it is both ways. Okay. The proof of this is simple, that if field is conservative, we know it can be written as a gradient of function. Okay, that means it can be written as partial derivative of some scalar function with x I cap plus partial derivative with scalar function with y j cap plus partial derivative with scalar function with z k cap. So if we compare these two, then m can be written as scalar function derivative with x, n is scalar function derivative with y, and p is scalar function derivative with c. Okay, and because these components have continuous first partial derivatives, so if we differentiate them with x, y, z and so on, and rearrange, then you will end up with these equations. Okay. Okay, say I take two examples here. The first example is to prove how we can prove the field is conservative, and second, how we can calculate the potential function. Okay, so show that this field is conservative over its domain. Okay, uh, so field is like m times I plus nj plus pk. So this is m, the n and p. So if we can calculate first partial derivatives, and if this is holds, then field will become conservative over the natural domain, and its domain you can see is the complete space. Okay, so the natural domain of this field is complete space, which is open and simply connected. Okay. uh, okay so we can write what is m, n and p. Okay, m, n and p, and we can then differentiate these with respect to uh, components. If we calculate p derivative y, you can clearly see it is x. Okay, when we differentiate this with y, we will treat x and z are fixed, so p derivative y is x, and n derivative with z is also x, so clearly this first is satisfied. Okay, so p derivative y and n derivative z are equal, both are x. M derivative z and p derivative x, so m derivative z you can see is y, and p derivative x is also y, so this is also equal. Similarly, n derivative x, which is z, and m derivative y, which is uh, minus e power x sine y plus z. Okay, minus e power x sine y is z, and n derivative x is also z minus e power x sine y, so this is also equal. So clearly the component test holds, and so field is conservative. Okay. uh, Second example is that if field is conservative, then find the potential function. Okay, so it is the same example, and we have just proved that it is conservative. So how we can find the potential function? So this field is mi plus nj plus zk, and we know that if field is conservative, then field can be written as gradient of function. Okay, so we can write field as gradient of function f, and so if we have expand the gradient, we can write it in the expanded form as partial derivative f with xi plus derivative f with yj plus derivative f with zk. And if you compare these two, then I can easily write what is f derivative x, which is m, f derivative y is this n, and f derivative z is p. Okay, so we have the function partial derivative with x, y, z. Okay, now we can integrate them, and then we can find what is the function. Okay, so if I integrate this first equation with respect to x, okay, so holding the y and z as fixed. Okay, so the left hand side will be function of x, y, z, f itself. On the right hand side, we integrate with respect to x, treating y and z fixed. So exponential function integral is exponential, cos y is a fixed number. Okay, so ex cos y integral is ex cos y, and y is constant, so integral with respect to x is x, so x y z plus function of y z. Okay, so because y and z are fixed. Okay, so if I differentiate with respect to x, then this quantity will be 0, and we end up with the same equation. Okay, so we have integrated first equation. Now if I calculate the y derivative from this new equation and compare it with the second equation here, so y derivatives must be equal, and that will help us calculating this g function. Okay, so differentiating with respect to y and comparing with this second equation here. Okay, so f derivative y will be minus e power x sin y, which is already here. Okay, y derivative of this is xz, which is here, and so g derivative of y from here, partial derivative. So if I compare these two, then it immediately gives that partial derivative g with y equals 0. These terms will cancel out. Okay, and so if I integrate this with respect to y, then that means g is a function of z only. Okay, partial derivative g with y is 0 means g is not a function of y. Okay, so that means g is a function of z alone and it is not a function of y, so this above equation can be simply written as this. Okay, because g has to be independent of y. Okay, because this holds. Okay, and now again if I differentiate this with respect to z and compare with the third equation, then I can calculate what is g of z. Okay, so partial derivative of this with respect to z. Okay, so first term do not contain z, so it's 0 plus this, which gives xy plus g derivative with z. Okay, so if I compare these two, then xy plus z is xy plus g derivative z, which gives g derivative with z equals z. Okay, and then if I integrate this, and because g is a function of z only, so it will give g as z square by 2 plus a constant of integration. So I can substitute it back here, and that gives us the potential function fxyz as e power x cos y plus xyz plus z square by 2 plus a constant. Okay, so in fact we have calculated infinite number of potential functions for this vector field f. Okay. Okay, so now the Green's theorem. Okay, and there are two forms of Green's theorem. One is the tangential form and other is the normal form. The tangential form is also known as the circulation curl form. Okay, and it says that let C be a piecewise smooth simple closed curve enclosed a region R in the plane. Okay, before we go that, we know that if there is a curve piecewise smooth, we already know that that means what is smooth and what is piecewise smooth. Okay, so uh, it has continuous partial derivatives. Okay, along this, and simple closed curve. Okay, so these two points are important here, that the curve has to be simple as well as closed. Okay, for example the circle or triangle or rectangle. Okay, those curves are closed as well as they are simple. Okay, by simple means that the curve do not cross itself. Okay, uh, like if I create a curve like a sign of infinity, okay, or 8, then that curve is closed but not simple because it crosses itself. Okay, but like circle or a rectangle or square or triangle, these curves are closed as well as simple because they only meet at the end points. They do not cross itself in between at interior points. Okay, and there can be curves which are simple but not closed. Like if I simple create a line segment, then it is a simple curve because it do not cross itself, and it is not closed. Okay, the endpoints do not meet at the same end. Okay, so simple open curve it will be. So we will have a simple closed curve like circle, triangles, rectangle, square, or any general shape where the curve do not cross itself and only meet at the end point. Okay, so let f be a vector field with m and n components in I and j direction, uh, having continuous first partial derivatives in the open region containing R. Then the counterclockwise circulation of f around C equals the double integral of curl f dot k cap over the region R. Okay, so the counterclockwise direction is the positive direction of circulation, and if you have a simple closed curve, then positive direction is treated to be the direction when we move along the curve, and the region lies to the left of the curve. Okay, so that means the counterclockwise direction. And it says that the integral m dx plus n dy over the curve is the uh, integral over the region R of partial derivative n with x minus m with y dx dy. Okay, the n derivative x minus m derivative y, this is the circulation density of the vector field f. Okay, and the uh, circulation curl uh, theorem, which we can use to calculate the flow in the xy plane using the circulation density. Okay, so it gives us the line integral for the flow in the xy plane. Okay, and we can calculate the line integral using the double integral of the circulation density. Okay, the other form of Green's theorem is the flux divergence, or the normal form. So again, let's see be a piecewise smooth simple closed curve enclosing a region R in the plane, and let there is a vector field with m and n continuous partial derivatives in the open region containing R. Then the outward flux of the field across this C equals the double integral of the divergence F over the region R enclosed by C. Okay, so the outward flux can be calculated as using the double integral of the divergence. Okay, so m derivative x plus n derivative y, this is the F, so it is nothing but divergence m derivative x plus n derivative y. Okay, so it can double integral of the divergence of F. With this we can calculate the outward flux across the curve C. Okay, so in the previous this was n derivative x minus m derivative y, which gives the circulation. Here it gives the divergence. Okay, so it calculates the there it calculates the circulation along the curve. Here it calculates the outward flux uh, across the curve, okay, in the plane. And the two forms are just equivalent. Okay, so if you just rewrite the terms, these two forms are just equivalent. Okay, uh, he gives a one example here that use the Green's theorem to find the circulation and flux for the vector field f given by this, and the region R is bounded by, say, unit circle where t varies from 0 to pi to complete that circle. So we have to find both circulation and flux, so we have to use both theorems. Okay, uh, here the f vector is mi plus nj, so m is x minus y, n is x, rt is xi plus yj, so x is cos t, y is sin t. Okay, and so for circulation, integral m dx plus n dy is equal to double integral of the circulation density, which is n derivative x minus m derivative y. So n and m are known, so n derivative x is 1, m derivative with y is minus 1, so it will add because there is another negative sign, so it becomes 2 times dx dy. Okay, and so 2 goes outside, and it will be a double integral of dx dy, which is the area, or we are talking about unit circle, so unit circle has area of pi, so this immediately gives that circulation about this curve is 2 pi. Okay, uh, for the flux we have to solve the line integral m dy minus n dx, which is equal to the divergence of function, which is m derivative x plus n derivative y dx dy, and again we can calculate these two from here. So m derivative x is 1 and n derivative y is 0, so this part is 0 and this is 1, so it gives double integral dx dy, and so again it is the area of circle, which is pi, okay, area of unit circle. So the circulation along the curve due to this vector field is 2 pi, and the flux over the curve due to this field is pi, okay. uh, I leave you with some practice question that find the circulation and outward flux when you are given a field which is bounded along a boundary region enclosed by the parabola and line in the first quadrant, okay, and find the circulation flux for this field when region is a square cut by line x is equal to pi by 2, y is equal to pi by 2 in the first quadrant, so also with x-axis and y-axis, and use Green's theorem to find the counterclockwise circulation and flux of field O and curve C, where field is given and region is the triangle bounded by these three lines. Field is given this, and region is a square bounded by these four lines, okay. So we close it here. In the next class we will talk about the surface integrals for the vector function, okay. Till then, have a very